All right, happy Monday, everybody. Glad to be back. I hope you all had a good week while I was gone. So a couple of things to note is I did grade your exams. They were not at the level that I was hoping for. So, but that's okay, right? Like, we're here to learn. So the thing that I'm going to have us do to try to make sure that we understand the material is test corrections, okay? So this is an opportunity for you to earn up to half of the credit back for what you missed. Now this is to be thought of truly as a learning opportunity. Okay, this is not a punishment. You should not approach this as like, I can't believe she's making me do this crap. Because if that's the attitude that you're going to take, then it's not going to be good for anybody. It's going to waste my time. It's going to waste your time. Okay, this is truly an opportunity for you to revisit the material and try to build the knowledge that wasn't quite there yet on test day. Okay, the good news is we have a quarter. Okay, so one day does not define our mathematical abilities. Now, when you look at the test corrections instructions that I put on Blackboard, they're very detailed. So it says for each part of the test what you're going to do, because it's not just write down the correct answer, right? There's some reflection and careful thinking instructions involved. And part 7, there was no part 7 on the test. And I'd actually encourage you to start with part 7. So part 7 is to read an article that I attached about a fixed versus growth mindset that can hopefully help you to think about like why this activity is being assigned to you and what you might gain from it, and then also how this type of activity could apply for you in the future when you get into a situation where you give a test and the class average is a 55, okay? So maybe start with part 7 and then go through the test, okay? I also strongly encourage you to make a point to come see me at some point this week to talk about your exam, okay? So if you can't make it to office hours, then send me an email with your availability and I'll try to find a time that I can schedule an appointment with you, okay? And then just a quick reminder, the Gift of Numbers proposals are due in 9 days. So if you haven't already formed a pair, right, because you're supposed to do this activity in pairs, you should find your partner and you should start looking through the Common Core standards and practices so that you can start developing your activity, okay? If you design a proposal and you want to give it to me early, that's fine. You can do that, okay? But if you haven't already started thinking about it, now is definitely the time, okay? Okay, so the other thing, of course, that I did yesterday besides grade your exams was grade your homework. And I wanted to talk about this particular problem because almost nobody actually did this problem, like to the degree that I would like to see you doing your homework. And so I thought maybe this would be a good opportunity for us as a class to practice, like, what does it mean to identify patterns? And how does one go about this crazy, mysterious activity? Okay, we're trying to take away the mystery here, okay? So, so this problem was asking us to find, or to think about this sequence of numbers, okay, so these are numbers, right, 1/2, 1/4, 1/8, etc., and think about what would be the nth term in this sequence, okay? Well, so a good number of people did tell me this, so maybe somebody can help me think about how did you think about this, okay? So how did you decide, or like what properties did you notice? What stands out to you about this sequence of numbers? Brandon?
It's double the nth term.
It's double the nth term.
Or twice as much as the nth term.
So is 1/4 twice as much as 1/2?
I think that.
Okay. So that's okay. So we're trying. So do you want to fix it or
1/n, 2n?
Okay, so you're trying to give me a formula already,
Yes.
which is fine. But that is different than what you initially started to do. So your first instinct was to compare terms.
Yes.
Okay? So you were comparing the value of 1/2 and 1/4. Okay?
I was comparing it to the 4.
Oh, you were comparing the 2 and the 4.
Yes.
Oh, I see.
That's how I got that.
Oh, okay. So that works, right? So, okay, so the 4 is twice the 2.
Yes.
And the 8 is twice the 4, and the 16 is twice the 8. Oh, okay. So for the first term, the denominator is 2 to the 1. For the second term, the denominator is 2 to the 2. For the third term, the denominator is 2 to the 3. You guys seeing this? So these are the denominators, which means that the whole fraction, well, luckily the numerators are staying pretty well behaved, right? So we could imagine getting to this, right? 1 divided by 2 to the n. Now some people, based on your homework, what I assume you did was you recognized that the first term was 1/2, and then to get each of the subsequent terms, you multiplied by 1/2. So I also saw a lot of people write 1/2 times 1 over 2 raised to the n minus 1. Presumably you would notice that this is in fact a geometric sequence with a common ratio of 1/2. Okay, now notice if we multiply 1/2 times 1/2 to the n minus 1, we get 1/2 to the n, right? But what is that? That's 1 to the n divided by 2 to the n. Well, what's 1 raised to any power? 1. So these are, in fact, equivalent representations. Is that okay? Okay. The sum part of the question is the part that it seemed most people just kind of surpassed. And so I want to talk to you. Okay, so like you see a question like this. It says, what is the sum of the first n of those fractions? What a crazy question to ask. Okay, how are we going to sink our teeth into this question? Well, one strategy would be to make a table, okay, where you actually experiment. What does the sum of the first of those fractions look like? Well, for the first guy, we're just adding, maybe that's not the best direction to do it in. Let me do a vertical table. So for the first guy, we're just adding 1/2, right? So 1/2, not very interesting. Now, when I want the sum of the first 2 of those fractions, that means I'm adding 1/2 plus 1/4. Okay, well, what is 1/2 plus 1/4? Well, I'd have to create a common denominator, right? And add those fractions. So I get 3/4. Okay, well, just having 1/2 and 3/4 is not quite enough for me to start getting a pattern going. Okay, so now let's see. Well, what is the sum of the first 3 of those fractions? So when n is 3, what am I looking at? I'm looking at 1/2 plus 1/4 plus 1/8. Okay, well now in order to add those, I'm going to need to create a common denominator again. Now I've already done this work, right? 1/2 plus 1/4 was 3/4. We've already done that. So 3/4 is the same as 6/8 plus 1/8, which is 7/8. Okay, now if we look at the sum of the first 4 terms, okay, 1/2 plus 1/4 plus 1/8 plus 1/16. Okay, well, we've already added the first 3. That was 7/8. So I want to add 7/8 to 1/16. So I'm going to create a common denominator of 16. So I'm going to have 14/16 plus 1/16. That's 15/16. Okay, so we've got 4 numbers so far. Let's see if we can start digging out a pattern, right? So when n was 1, the sum was 1/2. When n is 2, the sum is 3/4. When n is 3, the sum is 7/8. When n is 4, 15/16. Okay. Well, let's attack the denominators for a second. Let me rewrite that table just without all the scratch work. Okay, so these are the numbers that we're comparing, and we're trying to represent what would I shouldn't have made that so big. What would for n be, right? For the sum of the first n terms, what's the pattern? Okay, well, if we focus on the denominators, hey, the denominators were the same as what they were over here, right? For the first term, the denominator is 2. For the second, the denominator is 4. For the third, the denominator is 8. So we can handle the denominator really easily. The denominator is 2 to the n for each of those resulting sums, yeah? Is there anything that you notice about the numerator?
They're odd.
Okay, they're odd.
Multiples of 3? No.
7, not a multiple of 3. So 1/2, 3/4, 7/8, 15/16. So 1 less than the denominator. Okay, well the denominator is 2 to the n. So 1 less than that would be 2 to the n minus 1. This is the process. Okay? I would never in a million years expect you guys to look at the question as it was written and automatically know a formula. That is not the point, right? The point is we got to get our hands dirty. We have to actually come up and generate some examples, wrap our heads around what's going on, and then start asking questions, start playing with the numbers, okay? Identifying patterns. This is the activity, okay? So you guys had another set of homework problems that asked you to do a similar type of activity that was due today. Are you ready? Can I move on? Okay. So for today, you had some problems that asked you to find the sum of the first n even integers, and then establish some formulas, and then figure out the sum of the first n odd numbers, and then the sum of the first n terms in an arithmetic sequence. These were my rewordings of your homework. Okay, so the last 2 questions, I think, from your homework assignment. Now, the book tried to help you get this going, right? So the book said, well, for part A, rather than just asking this question, what is the sum of the first n even integers, they actually tried to push you in the right direction, right? They gave you a table. They said, let's organize this information. Okay, so they said, we're going to look at when n is 1, I'm adding the first even integer. Well, to nothing, right? I'm just looking at the first even integer. So well, the first one even integer is just 2, right? But when I look at the sum of the first 2 even integers, well, now I'm adding up 2 plus 4, which is 6. When I add up the first 3 even integers, 2 plus 4 plus 6 is 12. When I add up the first 4 even integers, 2 plus 4 plus 6 plus 8, that's 20. First 5, 2 plus 4 plus 6 plus 8 plus 10, right? And the goal is to say, well, when I look at the sum of the first n even integers, 2 plus 4 plus 6 plus 8, what will the nth even integer look like? How would I represent that? Ooh, so here's a good question, right? So these numbers, 2, 2, 4, 2, 4, 6, 2, 4, 6, 8, 2, 4, 6, 8, 10, 2, 4, 6, 8, 10, 12, those are coming from a sequence, right? 2, 4, 6, 8, 10, 12, right? That's what kind of sequence? That's an arithmetic sequence. Can we describe the nth term in that sequence? Yeah.
You have to multiply by 2.
Multiply by 2. Yeah, the nth term would look like 2n. Exactly. So when I'm going back up here and I'm thinking about the sum of the first n even integers, that's 2 plus 4 plus 6 plus 8 all the way up to plus 2n. And the goal of part A is to rewrite this very cumbersome sum in a nice compact way. So we're trying to find a rule, if you will, to produce the value of that sum, okay, for any n. Well, so now we're back to where we were before. We got to start looking for patterns, okay? So playing with the numbers, 2, 6, 12, 20, 30. Thinking about those numbers in relation to 1, 2, 3, 4, 5. Yeah?
It's n,
Uh-huh.
the number, squared, and then you add the number.
Okay, so I'm going to, so you said this, yeah? Another way that some people don't automatically think in terms of squares, that's a pretty sophisticated thing to do. Some people might have thought of it this way instead, right? And there's countless ways that you could have come to this conclusion, okay? Okay, so finding that formula, though, was the point of Part A. Okay, so tackling that pattern recognition was the point of Part A. Question?
Can you, I got the answer right somehow, but
Mm-hmm.
can you explain, like, how we got to that instead of just going directly to the answer?
Sure. Christine had a fantastic way, I thought. She shared with me in office hours. So she, instead of organizing the table vertically, organized it horizontally and started looking for connections between the numbers. And she noticed that 1 times 2 is 2. 2 times 3 is 6. 3 times 4 is 12. 4 times 5 is 20. 5 times 6 is 30, right? And so by the time you get to n, well, you have to multiply n times n plus 1 to get the value of that term, right? And so sometimes it's just such a simple thing as rearranging the information on a page to help bring out a pattern, right? So yeah, so that I really liked that as a strategy. Okay. Oh no, I can't delete anything because we're going to build off of what we have here. Okay. So all right. So now here's the thing. Once you figured this really nice compact formula in Part A, then Part B, now they ask you to use that information to establish a formula. Now you'll notice that this formula is one that we've already established. We talked about this, I think, last Monday, or maybe it was the Wednesday before. I can't remember, but we've already talked about how to establish this formula using Gauss's method of like adding the sums in reverse order, kind of thing. Do you remember that? That was a pretty cool strategy. Okay, well, it's not the only strategy, right? If it was, it wouldn't be that cool, right? So, okay, so how can we use the information that we have in order to establish this formula? Well, if we're going to use the information we have to literally start with the information we have. So what is the information we have? It says that 2 plus 4 plus 6 up to 2n is equal to n times n minus 1. This is what Part A tells us. My goal is to establish that the sum of the first n integers is n times n plus 1 all divided by 2. Okay. Well, that means I need to be able to manipulate this equation to look like the equation that I'm trying to establish, right? So check it out. If I look on the left-hand side, 2, 4, 6, blah, 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 2n, right? All of those numbers are divisible by 2. So I can factor out a 2, and when I do, I'm left with the thing I care about, right? This left-hand side of this formula is precisely what I get when I factor out a 2. Now, I haven't changed anything about my equation. Like, I haven't changed the value of the left-hand side by factoring out a 2. So this is still equal to n times n plus 1. Oh, but hey, the thing I was trying to establish is that this sum is equal to n times n plus 1 divided by 2. So what's going to be the icing on the cake? Divide by 2. on both sides, right? To maintain the relationship that we have here. Okay? This is the power of algebra, right? Is that we can, this is a beautiful mathematical argument right here. 3 lines to establish this formula. Okay.
So it wasn't right, like if you just, I just like this, I don't know, I just like plugged in like what I thought the next number would be.
Okay, so you came up with another case of like what if we went to like this, some of this first 6 even
Yeah.
integers? Okay. Well, so right, so certainly generating more examples can help you get to a pattern, but the goal here really is to be able to come up with a formula in general. So only looking at one case is not enough to establish generality, right? It's a good stepping stone. It's a good first step in your thinking process.
What I'm saying is like for part B,
Mm-hmm.
since it said use part A in algebra to show that, and then it gave that formula.
Yes.
All I did was like, I plugged in what I thought for the n, I plugged in the next number and like got like an answer for n.
What do you
That's not
mean, the next number?
You know, it said like 1 plus 2 plus 3 plus 4 plus and then dot dot dot.
Uh-huh.
Well, I just like, I plugged in, I just like assumed that we were going to do 5 next. So then I plugged in 5 for all the n's and then came up with like, basically like solved for n. But that's not, because I didn't
So
know
if
exactly what it was asking me to do.
Okay. Well, so this is what it was asking you to do. Okay. Does this make sense? So now for part C, it gives us a new formula to establish. So in part C, it's saying, let's establish this identity, that if I add 6 plus 12 plus 18 plus 24 plus 30 plus 36, all the way up to 6n for any n, that I should get the value 3n times n plus 1. Okay. Well, so how are we going to use what we already have? And unfortunately, at this point, I really do have to erase for space. So use part B to show this. Okay, well, so let me, before I erase, I'm gonna recopy this. But part B, the conclusion of part B was this formula, right? The formula that we technically already established on the previous day. Okay, just through a different explanation. So part B says, sorry, now I'm working on part C. Part B tells us that 1 plus 2 plus 3 all the way up to n is n times n plus 1 divided by 2. So this is something that we're going to use. But our goal really is to show that this sum is equal to 3n times n plus 1. Okay. So we're going to show that this left-hand side equals that right-hand side. That's the purpose. So let's start with the most complicated looking part of that statement. Let's think about the left-hand side. What do you notice about each of these terms? 6, 12, 18, they're really highlighted at the end, 6n, right? Each of those are multiples of 6, which means you can factor out a 6. Oh, wait, 6 times that sum, I know something about that sum, right? Part B tells me that the sum in those parentheses is equal to n times n plus 1 divided by 2. This is by part B. Does this simplify?
Yes.
Sure does. 6 divided by 2 is 3. Hey, that is exactly what we were trying to show that sum equaled. Okay. So this was just factoring out the 6, and this was simplifying. Right? This is all we're doing. Okay. Having gone through this process for these 3 examples, do you guys now feel like you might be able to tackle this next question? What is the sum of the first n odd integers? How would we get started?
Draw a table.
Make a table. That's a great idea. Okay, so in this table, we're going to think about the sum of the first n odd integers. Okay, so if I think about the sum of the first 1 odd integers, well, what's the first odd integer? 1. Okay. Sum of the first 2. So now I'm looking at 1 plus 3. So 1 plus 3 plus 5. 1 plus 3 plus 5 plus 7. 1 plus 3 plus 5 plus 7 plus 9. Okay. Anything standing out to you guys?
Squares.
They're squares. So if I were to think about the nth, the sum of the first n, what's my hypothesis? What do I think? I think I'm going to get n squared, right? Because this 1 was 1 squared. This 4 was 2 squared. This 9 was 3 squared. This 16, 4 squared. This 25, 5 squared, okay? So if there's justice in the universe, right, then the sum of the first n odd integers will be n squared. Okay. Questions or comments about that? Now the last thing that I have written up here was again about was technically question 14 in that section. It asked for the sum of the first n terms in an arithmetic sequence. And again, it had a table, right? So it was saying, you know, I'm going to have the first term is just a, the second term is going to be a, or sorry, the sum of the first, oh, I think they actually did list out what's the term and then the sum of those terms. I think that's how they did it. So a plus d, the sum is just a plus d is 2a plus d, right? 3 is a plus 2d, so a plus d plus a plus 2d simplifies to 3a plus 3d, and they kept going, right? So in general, when we look at the nth term, we're looking at a plus n minus 1d, and the sum, a plus d plus a plus 2d plus a plus n minus 1d, right? Like that's what it will look like. Okay, but that's horrendous. Nobody wants to deal with that, right? That's not going to help you figure out the 200th term in an arithmetic sequence with initial value 3 and common difference 2.7. Like, you're not going to do that. Okay? So the goal here, again, is to establish a formula that will simplify this. Okay. Well, let's look at this sum. So each of the terms in this sum has an a in it, right? So how many copies of A are in the whole sum? How many terms are there in this last line? There's n terms, right? So that means there's n copies of A. Now, the first term doesn't have a D, right? But the rest of the terms do. So D, 2D, 3D, 4D, all the way up to n minus 1D, right? So let me actually... So I could think about that as in 0 plus 1 plus 2 up to n minus 1 D. Okay, well, adding 0 is not a big deal. I can basically ignore that, right? So what am I looking at in these brackets? 1 plus 2 plus 3 plus 4 plus 5. We're looking at the sum of the first n minus 1 integers. Wait, that seems oddly familiar, right? Do we have a way to express the value of the sum of the first n minus 1 integers? We do, yeah? That's literally what we just did here. Except this sum was going all the way up to n, right? And we only want to go up to n minus 1? Well, that's the beauty of a formula, right? If I substitute n minus 1 instead of n, what do I get? I'll have n minus 1 times n minus 1 plus 1 over 2d. Where what I did was, instead of going all the way up to n here, I replaced n with n minus 1, and I did it in both places. Does that simplify? Yes. Right, this is n times a plus n times n minus 1 over 2d. Okay. And so now we have a really nice compact formula for the sum of the first n terms in any arithmetic sequence. Right? Literally, we could now take any arithmetic sequence where, as long as we know the starting value a and the common difference value d, we can compute the value of the 17th, like the sum of the first 17 terms, the sum of the first 301 terms, the sum of the first million terms. We can do that now because we have this really nice compact formula. Okay? The power of algebra. Okay. Okay. So does this give you a sense of like what the homework has been about in terms of patterns and formulas? Like why we're doing what we're doing, how we're doing what we're doing? Does this help? Is this a good use of time? Yes? Okay. Okay. Well, you'll notice a couple of times as I was going through that conversation, I kind of flubbed up my words a little bit. It started out by saying like the sum of this, right? is a mouthful to describe all of the things that we're just talking about. And so what we're about to do is transition into section 12.4, which talks about function, okay? And is going to give us a much easier way to communicate, okay? So functions in algebra. Okay, so functions are probably one of the most dominant topics in K-12 schooling mathematics, like for the last 30 years. Okay, so your students will start working informally with this idea as early as kindergarten, and then it becomes like much more obvious that you're dealing with functions starting in grade 4. When you're looking at generating and analyzing patterns, so what we were just doing. Grade 5, analyzing patterns and relationships. Grade 6, representing and analyzing quantitative relationships between dependent and independent variables. So they start really formalizing these notions leading into middle grades, okay? And oftentimes, textbooks will introduce the idea of function via patterns. So everything we just did can be reconceptualized in terms of function, okay? And so, so we're gonna basically mimic the process that we just did, only with numbers instead of letters for a minute. So okay, so I want to think about a sequence of numbers: 9, 30, 51, 72, and so on. Okay. And I want to ask myself, is there an identifiable pattern present? Well, can you guys predict what is the fifth number going to be in this sequence?
93.
You say 93. Why do you say 93, Brandon?
Because it's an arithmetic sequence of adding 21 to the end.
Oh, okay. So you add 21 here. You add 21 here. That seems pretty convincing. So if I add 21 again, we'll get 93. Okay, cool. So that's the type of activity that we've been doing. Let's formalize it. Okay, so again, just a different way to represent a vertical positioning where we observe that we're adding 21 each time. So if I add 21 once more, I'll get that value of 93. But here's the thing. Location and list, actual number, pattern description, these are all very wordy ways to communicate. And our goal is ease of communication, okay? So let's take that information, introduce variables, and algebraize it, okay? So instead of location in the list, I'm going to use n to represent that, okay? So n represents the location in the list. S is going to represent the value of the number in that position, okay? And what I want to do is to actually describe a formula now, or a rule, if you will, that will tell me if I give you a value of n, what will be the corresponding value of s. So you guys have been doing this already. Help me out. So how can I describe this relationship between s and n? I'll get a value of s. In what way? Brandon already said it was an arithmetic sequence. So how do I get to the like nth term in an arithmetic sequence?
Nine plus.
So what's the 9 represent? So I start with a number. To get subsequent numbers, I have to add copies of the common difference, which we can very clearly see is 21. So to get to the second number, I had to add 1 copy. To get to the third number, I had to add 2 copies. To get to the third number, I had to add, wait, what did I just say? To get to the fourth number, I had to add 3 copies, right? So I'm adding n minus 1 copies of 21. So what we've just done is represent a relationship, okay? This relationship right here describes how values of n and s are related to each other, okay? For this particular pattern, this particular arithmetic sequence, and this choice of variables, okay? I could have chosen other letters as my variables, and and that would not really create any sort of difference. Now, if I change my arithmetic sequence, then we would have to change our formula, okay? Because there would be a different relationship present, okay? Now, this relationship between values of n and values of s was a very special one, right? In that to each value of n, there was precisely one value of s that corresponded, right? So for each of these values, there was only one value corresponding, okay? We call those kinds of relationships functions, okay? So this is the definition that our book offers a function from one set to another, noting that it may be the same set, okay? Is a correspondence in which each element of the first set is assigned to exactly one element of the second set, okay? So your book had some really nice examples, and it's such an important conversation to have that I wanted to go through basically all of the activities in the book in class today. So here was their first sort of check on understanding activity, okay? So just to make sure we're all on the same page, right? Because these are like kind of special to mathematics types of representations. What's being represented here? Well, the circle is signaling that this is a set. And the points with the corresponding numbers are saying these are the objects in that set. And then we have an input set and an output set. The arrows are meant to represent the correspondence. So 22 corresponds to 97, 27 corresponds to 22, and 40 corresponds to 114 in this first example. So that's the way that this image is meant to be read. I'm walking you through this, right? Because if you give this to your students, they might look at this and be like, what on earth is this representing, right? These are sort of conventions that we establish in mathematical classrooms. That, like, that's how you read this picture, okay? So if that's the way that we read this picture, the question now is, does this image depict a relationship that satisfies the definition of a function? So is this representing a functional relationship? Yes? Okay. So let's see. Does it represent a correspondence from one set to another? One set to another, arrows all going in the same direction. So far, so good. Okay. Does each element in the first set get assigned to something? 22 gets assigned, 27, 40, they all get assigned to something. Now, do they get assigned to exactly one something?
Yes.
Yes. Okay. So yes, this does, in fact, depict a functional relationship. What about the second example? Does this depict a functional relationship between the input and output sets? So I heard a no. Can you explain why?
Because 10 is given to elements from the second set.
Okay, so 10 corresponds to both 6 and 14. So we're violating this exactly one element principle. Okay. What about the third example? Does this depict a functional relationship? Yes?
No.
No. So let's go back to the definition. What does the definition require? A correspondence in which each element of the first set is assigned to exactly one element in the second set. So what's missing?
The 4.5 is going to assign something.
Exactly. 4.5 is missing an assignment to an element of the second set. Okay. Now, if we had assigned 4.5 to 6, for instance, would that now be a function? That's okay, right? Well, so it's okay for the reason that 4 is an example. So is 4 a functional relationship? Representing one? Yeah, right? Each element gets assigned to a value in the output set and gets assigned to only one value in the output set. Now, what are your students going to get tripped up on? Yeah, they're going to focus on the fact that there's two elements here going to one element here. It's perfectly okay, right? The directionality of this relationship matters. And so you just bring them back to the definition. Okay, so each element in the first set gets assigned to a unique element here. It is not, like the reverse does not have to be true. Okay. Okay. So I really like this number 5 though. So okay, let's take it out of the abstract and let's give a context. Okay, so if we were thinking to each postage stamp, assign the weight of the first class letter that the stamp will pay for, that's the correspondence we're trying to define. Okay, so as an example, a 45-cent stamp will pay for weights up to and including 1 ounce. So our goal is to decide, is this correspondence a functional correspondence? Does this describe a functional relationship? You say no? Celine, why not?
Because the 45 cents can be assigned to anything that's under 1 ounce, like several things that are under 1 ounce, and it could be assigned to 1 ounce as well.
So there's something, right? That 45-cent stamp could get assigned to any of those values, and in fact, infinitely many more. Right? So, okay, super. Could we describe a functional relationship in this setting? Is there a way to tweak the correspondence so that we do have a functional relationship?
If you flip the ounces as the first set and then have the value as the second set.
Okay, yeah. So if we change the directionality, so let's consider the weight of the package to be the input set and the corresponding like price of the postage to be the output set. Now we have a functional relationship. Okay, super. Okay, other ways your students will be asked to think about functional relationships is in 6 and 7. Okay, so here we have a collection of ordered pairs. Again, we're mathematically sophisticated, but let's just break down the ways to interpret these. So when I read 0, 1, 1, 2, 2, 3, 3, 4, how should I be thinking about these ordered pairs? What's the convention that we use to talk about these? Like, what is the 0 representing and what is the 1 representing?
X, Y.
Input, output, right? This is a convention. It's a convention I kind of detest, but it is a convention. My reasons are when they get into upper level mathematics in high school, if they have to study polar coordinate systems, so think trigonometry, this convention goes away and it becomes problematic. But nonetheless, this is the world we live in. So, okay, so let's live in it. So yes, so when we look at these ordered pairs, the first coordinate typically is thought of as the input variable. The second coordinate is representing values of the output variable. So when we look at this grouping of ordered pairs, are we looking at a functional relationship? Yeah? What would be the output corresponding to an input value of n? N plus 1. Super. The fact that you could tell me that, there was something really powerful that just happened. I said, what would be the output corresponding to an input of n? And you were able to tell me, right? It will be n plus 1. The fact that you could say that is what means that you have a functional relationship. Okay? You could tell me the unique value corresponding to an input of n. Okay? What about this last set of ordered pairs? So I'll write them bigger. 2, 5, 3, 8, 2, 9, 510. Do we have a functional relationship? No? Yes? No.
2 is assigned to 2.
Oh, I have the same input value, 2, assigned to 2 different output values. So we could, you know, if you were trying to support your students in making connections, you could draw this picture again with the circles. And so you would have a 2, you'd have a 3, and you'd have a 5, and 5, 8, 9, 10, right? And you would see that this 2 goes both to a 5 and to a 9, right? You could draw that picture for your students. Okay. What about this, number 8? So in words, we're describing that every number is paired with its square. So 1 is paired with 1, 1/2 is paired with 1/4, 1 2/3 is paired with 25/9, the square root of 2 is paired with 2, etc. Is this describing a functional correspondence? So in words, every number is paired with its square. So if I take a number, it will be paired with its square. The fact that we could just do that means that we in fact have a functional relationship. What about this? In any classroom, associate with each first name a student's full name. Here's part of the class roster. Emily, Emily Dickinson. Memo, Memo Flores. Rachel, Rachel Hobbs. Emily, Emily Brunt. John, John Sinclair. Functional relationship? No? Why not? 2 Emilys? And those are not the same. Right? Okay, so now if you're a teacher who wants to double check, so you want to check your students on the fly. If my students told me there's 2 Emilys and that was their reason, here's what I would come back with. Here's a new set of ordered pairs. Do I have a functional relationship? I do. Oh, but I have 2 2s as input values. Both of those 2s are being assigned to the same number. Okay, so just the fact that the same input value appears twice is not a reason to automatically say this is not a function. Okay, it's the fact that the input appears twice and corresponds to 2 different output values. That's what makes this not a function. Okay, super. Okay, so I said that a lot of textbooks will introduce the idea of function by building it out of pattern recognition. Okay, and so the way that this is often worded is, what's the rule that would produce this relationship? Okay, so here I've got 3 tables, and I'd like us to try to decide what's the rule. Okay, so to get a correspondence between 3 and 60, something and 40, 5 and 100, okay, what rule could give me that? Do you have an idea? Multiply by 20? Do you guys agree? If I multiply by 20, 3 times 20 is 60, 5 times 20 is 100. Okay, so 20 times 20 is?
No.
400. 20 times 100, 2,000. Ooh, how do I get this guy? Divide by 2. Okay, so the rule was multiply by 20. Okay, what about here, second table? What's the rule?
Add 46.
That definitely works there. Does it work here? Oh, it does. Cool, so that's promising. So what number do I have to add 46 to get 80? 34. Okay, if I add 46 to 629, 675. And what number do I have to add 46 to get 100? 54. Great. Okay, so the rule is add 46. This one's a little harder. So adding 1 works for the first two, but then it fails on the third one. Can't multiply 0 times anything to get 1. So it's not that simple. We have literally just eliminated the possibility that you could simply add or multiply. So it's either a combination of those two things, or we're going to have to get some powers involved. Well,
N plus 1.
n plus 1 squared
Okay.
or n plus 1. So n plus 1 fails here, right? So 2 plus 1 is only 3.
I was thinking about the third term. 3 plus 1.
I didn't know what the rule is, but from what I can see,
Uh-huh.
the n to the power of what the input is would be the output. So like n, the first term would be 0.
Mm-hmm.
So if it's like n is 1 to the power of 0 equals 1.
Okay.
And then 2 to the power of 1 equals 2, and 2 to the power of 2 equals 4.
So you said 2 to the 1 is 2, 2 to the 2 is 4. So if I'm thinking about that as my pattern, I would say 2 to the 0 is 1.
Yeah.
Are these all true statements?
Yes.
Does that work?
Yes.
So if we think that's the rule, so the rule we're saying is 2 raised to the power of the input value, right? Okay. Oh, but wait. That's not the only way to do that. So less obvious, I could have also have said, well, if I take this number, the input number, and I square it, and I multiply it by 1/2, and then I add 1/2 of its value, and then I add 1, I will in fact also get this set of numbers. Right? So 1/2 times 0 plus 1/2 times 0 plus 1 is 1. 1/2 times 1 plus 1/2 times 1 plus 1 is 2. We could play the same game. Okay, so this is meant as a word of warning, right? Which is that when you're building a rule from a table of values, you are limited, okay? You can identify patterns and develop a rule, but in the absence of context or other information, you have no way of knowing if your rule is, quote, the rule, right? Okay. So this is just a word of warning. This is not to say never look for patterns and never describe rules. It's not at all the message. It's just a cautionary tale. Your rule might not be the only rule. Okay, there may be other rules that describe the relationship that's depicted with a limited set of data points. Okay? This, by the way, is how like politicians try to deceive us by only giving us a little bit. Anyways. Okay, another thing to keep note of, right, is that I just erased all of it. Was multiplying by 20, adding 46. That's all well and good and fairly easy to say, but when it got time for me to describe the rule for the last table, that again got a little convoluted in the wording, right? We're not going to stand here, and especially when I had to say 0.5 times the square of that number and 0, and that was gross. So what did I do as I was saying that out loud? I wrote down an algebraic expression to convey that information. Okay? And so we have developed a notational device to do this. Okay? Function notation is incredibly powerful. It allows us to capture a lot of information. Okay? So sort of the nitty-gritty of it, right, is that you have a function name. So this f is the name of a function. It's saying it's representing a relationship, okay? Giving a name to a relationship. F parenthesis x parenthesis, that collection of symbols is representing the output of a function when the input value is x. Okay? And on the right-hand side is the defining rule. The right-hand side tells you, given a value of x, here's how you would actually compute the value of that output. Okay? So thinking back to our examples here, we had multiply by 20. Well, if I let my input variable be called x, my output variable or output value will be some f of x. I can define f of x is equal to 20x. Right? And so technically, in this box, I could have written this type of information just as easily as the corresponding values. Okay? So the powerful thing about function notation is I could literally write f of 20 and know that that represents the output of this function f that's describing the relationship between input values and output values under the relationship where outputs are determined by multiplying inputs times 20. Okay. Likewise, I could define a function. I'll call this function not f again because I've already used f. I don't want to confuse myself or my students. I'm going to call this function g, and I'm going to define output values of g by saying, let me add 46 to my input. Okay? And again, I'll define a new function. I'll call this one h, where I say raise 2 to the value of the input. Okay? So again, this 1 is really h of 0. This 2 is h of 1. This 4 is h of 2. This 150 is g of 104. Right? So you might be saying, well, Stacy, this seems really silly. Why bother? Well, in these examples, yes, it might be a little silly to introduce function notation because we have just numbers, right? We have really concrete numbers to work with. But the power of function doesn't come from the numbers. The power of function comes from the representation of a relationship. Okay? So we can talk about relationships without ever even knowing what the rule is to explicitly describe that relationship. Let me give you an example. And unfortunately, my I have to do it on the fly because all of my old files, my old computer, got wiped. So, yes, really sad. Okay, but so I want you to imagine this, the following scenario. You take a pebble and you drop it into a still pond. What's going to happen? It's going to form a ripple, right? And that ripple will grow as time elapses. Yeah? Okay. Well, in that situation, I could ask a question like, what's the area of the ripple formed as time elapses? Okay, so we imagine dropping this rock, pebble, whatever, into a pond, and the size of the ripple grows, right, as time elapses. But I haven't given you enough information to really, like, I haven't told you whether or not that ripple's radius grows at a linear fashion. I haven't told you how this is working, right? But I'd argue that you can still talk about and represent this relationship symbolically, okay? So in particular, what do you notice about the ripples that are formed? What kind of shape are they? Circles. Do we know anything about the area of a circle? We sure do. Area of a circle is given by this formula, okay? Well, if I want to represent the area of the circular ripples formed as a function of elapsed time, well, I can conceptualize that by thinking about the fact that the radius itself is changing as time elapses, right? So 3 seconds after, or like 0 seconds from when the pebble hits the surface of the pond, the radius is 0, right? But then as time elapses, it grows and gets bigger and bigger. Okay. Well, I could use a function to represent the length of the radius at t seconds since the pebble hits the pond. And I can let g of t represent the area of that ripple, right? And so if I think about the area of the ripple for any time t, that's going to be pi times the size of the radius squared. Now, this is crazy complicated looking, right? But it's actually not that bad, and it gives me a lot of power in the sense that if you ask me, well, what's the area of the ripple at 5 seconds? I can answer that really fast. The area of the ripple at 5 seconds is g of 5. If you ask me how much has the area grown between 5 and 10 seconds, I can answer that just as fast. At 10 seconds, this is the area. At 5 seconds, this was the area. The difference of those areas would tell me how much the area has grown. Function notation allows us to communicate without ever having to actually compute values in this circumstance where we don't know values. Okay? You can still talk about a situation powerfully. This is really cool stuff. Hopefully I've convinced you that it's cool. I think it's fantastic. Okay. Now, maybe one of the things that you might not be convinced that it's so cool of yet is the fact that so much of the work we do is based in equations where we use a y sort of in place of the f of x. Okay? And what I'd like to do right now is convince you that the function notation is so much more powerful than just using the variable. There's a time and a place for that variable. So what I'm talking about right now is the difference between saying y equals x plus, maybe let's make it more complicated. What's the difference between these two things? Why might we prefer one over the other? When would each one be appropriate, etc. Right? We're definitely going to have this conversation again at some point. But right now, what I'd like to convince you is that this second form is really useful if you want to be able to communicate quickly about the correspondence between input and output. So, what do I mean by that? I mean, if x equals 1, then y equals, 16? Is literally the entire sentence that you would have to say to tell me the relationship between x and y when x is 1, given this information. To communicate the same information using function notation, all you would have to do is say f of 1 is 16. It's a tighter notation because this, whatever's inside the parentheses, is communicating what the input value is. And this set of notation tells you the corresponding output. When we tell you a value that that's equal to, now I know when the input is 1, the output is 16. Okay? It's a really nice compact way to do it. Whereas up here, if you say y is 16, my question is going to be all the time? That's shocking, because that's not a constant number, right? So, okay. Did this make sense? No? I'm sorry? Not this part? The difference between using y and f of x? So all I'm trying to say is that function notation will allow me to communicate two pieces of information simultaneously, right? F of 1 equals 16 communicates the input value is 1, its corresponding output value is 16 under this relationship. So I guess actually it communicates three things. It communicates which relationship you're thinking about, an input value and an output value, all at the same time.
Can you write that down?
Function notation communicates three pieces of info simultaneously. 1, the relationship name. 2, the input value. And 3, the corresponding output. Okay, so function name is f, input value is 1, corresponding output value is f of 1, which has a value of 16. Okay? In order to communicate all of that information without function notation, I would literally have to write down this equation, y equals x squared plus 5x plus 10, and when x equals 1, then y equals 16. You have to write down all of that information to communicate the same as what is conveyed with f of 1 equals 16. Okay? Okay. So before I started talking explicitly about function notation, I had put up a word of warning, which was when you're using tables to generate functions, right, to generate rules, you have to be careful because a set of values could potentially be described by 2 different rules, or more than 2 different rules. You can essentially always define at least infinitely many. Okay? So, all right, so that might not be the best place to start with your students, okay? Now, what might be better? Giving them a context, okay? So you could start with a simple activity where you want your students to build a row of squares, okay, out of toothpicks, and describe the phenomenon that's happening, okay? So your student Pat, he made a pattern of squares from toothpicks, and he generated the following instances, if you will. So he's got 1 square here, 2 squares, 3 squares, and 4 squares, okay? And the goal is to identify, the ultimate goal will be to identify a relationship between the number of squares and the number of toothpicks. So my question is, how many toothpicks will Pat need to make a row with 40 squares? And then 100 squares, and then n squares. So we want to think through this. So here's a situation in which we could in theory work with toothpicks and start generating examples to save space and time. Toothpicks. We're going to encourage you to draw pictures on your paper instead, where you can use the images already up here. You might, if you want, feel the need to generate some more examples. But we want to think through this. Okay, so how might we determine 40 squares is a lot of squares? I probably don't want to draw that many on my paper, right? Like instantly, I've already forced you to think about how are you going to generalize from the examples given to bigger numbers, because 40 is just too many. It's too many, right? So you could maybe start with a table, right? You can make a table. That would be one way. And so in your table, you might want to connect the number of squares to the number of toothpicks. So when we have 1 square, how many toothpicks? 4. When we have 2 squares, how many toothpicks? Were there 7? 3 squares? 10? 4 squares? Did you say 13? 14? What? 13? Okay. Is there an identifiable pattern happening? 3n? What's n? Okay, so if I have n squares, plus 1. That was pretty easy. You guys got that fast. Cool. Okay, so if n is 40, right? Then according to this formula, we should get 3 times 40 plus 1, so 121 toothpicks. And when I have 100 squares, that would suggest that I should use 301 toothpicks. And then, of course, we've been using this formula to generate all of those. Okay. So how could I define a function to communicate this information? Question?
Oh, no.
Or are you going to answer? Oh, super.
I was gonna answer.
Excellent.
So it would be the function of n
Okay.
is equal to
3n plus 1. Okay, so this would be a perfectly acceptable way to do it, as long as you said let n be the number of squares, then f of n gives corresponding number of toothpicks. And now we have fully defined our function f. Okay. Did I have to use the letter f? I could have used G, H, K, L, M, N. Maybe not O, because people confuse that with 0. That looks weird. There are some that just maybe you don't use. They look weird when you use them. Okay. Super. Now, question.
In the beginning of class,
Mm-hmm.
you had did like, I guess, I don't know if it was a formula,
Mm-hmm.
but I don't know how to describe it, but I don't know how to piece together the formula. So
Okay.
what I did by just like staring at my
Yeah.
homework for a long time,
Yeah.
I figured out that I would just subtract the first number of toothpicks minus the how many times I multiplied it by, so 3, and that's how I got +1. Does that make sense? But I
Can
don't
you
know
say
if
it
there's
again?
an easier
I didn't get
formula to do that on all of them because I did the same thing, but I'm pretty sure that wasn't a formula. So I did, so 4 to get to 7 you add 3, 7
Right.
to get to 10 you add 3.
Great. Yes.
So I did the first number
Yes.
minus 3, 4 minus 3, so that's how I got the +1. So first I did 3n,
Mm-hmm.
and then I got the +1 by subtracting the first initial number, which is 4, minus 3, which, and I got 1. And then so now I know I multiply by 3 to n, and then add the 1. But I know that's not the way to do it. I don't even know how to explain that, but it does work on all of them. So I'm saying if there is a formula to get that.
So technically the formula that we already have to deal with this pattern is starting value plus common difference times n minus 1, right?
Okay.
That's the formula that we have established. Now, technically, if you manipulate this, it will in fact give you the computation that you did, right? Oh wait, no. No, it doesn't. I don't know how to, I'd have to think harder about whether or not, wait, why did you do 4 minus 3? No, you didn't. You did like, you said you did 7 minus 4 to get 3? No. What did you do?
She said she did 4 minus 3.
Why did you do 4 minus 3?
Because I just
Because 3 was the number that you added to get the 0th term, maybe? Yeah.
I
think that's-
just didn't apply that earlier formula to it. That was just my question. I didn't do that.
Yeah, that's exactly what she did. So what you did does work. Yeah. Just, I don't know if this will make sense because I don't know if you think in these terms or not. Essentially what you just did was put it into this form. I don't know if that means anything to you or not yet. Not yet?
I like that more.
We'll get there. We're not there yet. So I'll try to remember to bring it back to that when we do get there. Okay, now here's the thing. Here we are again, where we have a list of examples, right? Set of data points, and we've created a rule. Now, I've already given you an example where I was able to come up with 2 different rules to explain the same set of data points. So how can we convince ourselves that this really is the rule to describe this phenomenon? Okay, well, the book had some excellent discussion points about that. So I'd like to visit them. okay? So they gave a whole bunch of different justifications that students might offer you. So here's the first one. I needed 4 toothpicks for the first square, and then 3 more for each. Oh, sorry, let me start over. They were answering the question, how many toothpicks would you need to build 100 squares? Okay. So start with 4 toothpicks for the first square and 3 more for each of the 99 remaining squares after that. Okay. So I got 301. I think that's the number we got. So we got the right answer. But the real question is, do you find this argument convincing? And if so, how would you mathematize it? Okay. What function, if this is a valid argument, would capture this way of thinking?
4 plus 3 and minus 1, which is 99.
Oh, so, yeah, so basically, right, 4 plus 3 times 99, yeah? Okay, but that's not for anything in general, right? So if we were to believe his argument, do we believe his argument? Does it seem valid? I start with a square. In order to build more squares, I add 3, and then I have to add 3 again, and then I have to add 3 again, right? That seems pretty legit. I'm convinced. So in general, if I wanted to represent what he's doing, that would be the function to capture his way of thinking. Okay? Is that the same as the rule that we came up with? Well, it's not identical, but it's equivalent, right? Okay. Here's a different justification given by a different student. Nadia said, I checked 2 more cases and they worked, so it has to be right. Is this a convincing argument for why 3n plus 1 gives a rule for the number of toothpicks used in terms of the number of squares? So she checked it for 5 squares and 6 squares. Is that convincing? To claim that for any number of squares, I will know this formula works. So this is where mathematics differs from a lot of our common day experience, right? So just having 1, 2, 3, 4, 5, 6 examples by no means is sufficient for a mathematical argument, okay? Because there's a lot of underlying things that could happen. So this would not be considered a valid mathematical argument. We call this proof by example. That's not a valid proof technique, okay? You can prove something is not true by example, but you can't prove something is true by example. Examples allow you to generate patterns and make hypotheses, but they do not prove anything, okay? So, okay, this student says, I put down 1 toothpick, and then every time I put down 3 more, I got another square. So to get 100 squares, I'll start with 1 toothpick, and I'll add 3 more 100 times. Does that work? I start with 1 toothpick, and I add, or I guess
There's no need for that.
Sorry, my cell phone just tucked at me, and I don't know why. So I started with 1, and I add 3, and I got my first square, right? And then when I add 3 more, I get another square. When I add 3 more, I get another and another. Right? Does this explain this phenomenon?
Yeah.
Start with 1, add 3, now I have a square. Add 3 more, now I have 2 squares. Add 3 more, now I have 3 squares. Does it work?
Yeah.
This works. This is a viable justification. Okay? How do we mathematize it? What would this student's function look like? Exactly. That is how this student is thinking about this phenomenon. Okay? This student is imagining having 100 squares already and says across the top there's going to be 100 toothpicks. In the middle there's going to be 101, and across the bottom there's going to be 100. So altogether there will be 301. Does that work? In the case of 100 squares? Well, did it work in the case of 4? Across the top there are 4. Across the middle there are 5. Across the bottom there are 4. Will that work as you build it out to 100 squares? It does, yeah? This is a completely acceptable argument, okay? Now, how would you mathematize Paloma's argument? Her function would look like what? So n is the number, n represents the number of squares. What is she saying? She's saying, let me think about how many toothpicks are on the top. How many toothpicks are on the top of n squares? N toothpicks. Let me think about how many toothpicks are in the middle. How many toothpicks are in the middle? N plus 1. And how many toothpicks on the bottom? N. Here's another student. 100 squares would take 400 toothpicks if I were to create them individually. But I'm not creating them individually, I'm smashing them together. So I'm going to have to take away 99 toothpicks from the middle when I smush them together. So I'll get 301 toothpicks. Does that work? Do you see how it's related to the images already there? So that's what it would look like if I built 4 squares individually, right? But I'm not. So I have to take away those 3 extra toothpicks to get the final image for 4 squares. It works the same way as you expand. So if we were to mathematize, how is the student imagining the situation?
+400 plus n minus 1? No, wait, minus.
So when n is 100, they're thinking 400, and you said minus n minus 1 when it's 100. That's what he did? Yeah. So I would say he's imagining how many toothpicks to make n squares independently, and then removing the appropriate number of toothpicks from the middle when he smushes them together. So why am I sharing this with you?
Yeah.
Hmm?
They all end up at 3 and plus 1, which you simplify.
Okay, So 4 different students generated 4 different rules to describe one phenomenon, and each student gave a perfectly viable explanation. Now, you're going to have a class of, what, 25, 35 students? Hopefully not 35 students. Your students will do this to you, right? Because they're creative thinkers. They will all come up with different ways to explain what it is they're seeing and doing. And so you're going to have the ability to evaluate what each person did on an individual basis and see, is this viable? And is this valid, right? So each of these different rules do, in fact, simplify to the same expression in terms of n, right? 3n plus 1. And so that would be one way to convince yourself that these students were doing viable things. But of course, before we could even get that far, in order to check that all of these rules simplify to 3n plus 1, we had to translate their thinking into formulas, right? That was the activity we just went through. Okay. Now, just again as like a practice, if you will, with function notation, when I ask you to describe what each component in the above definitions are, what I'm asking for is for you to be able to tell me that f is the name of a function relating number of squares to number of toothpicks, that n represents the number of squares in the row, and that, 4 plus n minus 1 times 3 is the rule explaining how to compute output values. So that's what I mean when I ask you to break down the components in each of these function definitions. So I want to know the name, the input value, the fact that f of n is the output value, and this is the defining rule. So I should have said that f of n represents output when input is n. Okay. And again, the activity that we just went through, where like these rules did not just pop out of thin air. They literally came from us translating a situation that was given to us in words into mathematical symbols. Okay. That activity is the purpose of the next section, 12.5. Using algebra to quantify relationships. Okay. Describe quantitative relationships. Okay. So, right, this 4 has a meaning. So that student, this 4 represented the number of toothpicks in the first square. This 3 represents the number of toothpicks you have to add to each square. This n minus 1 is the number of times you have to add 3 toothpicks to make n squares. Each of these terms means something. Okay? So I could just as easily ask you to do that on, say, the next quiz. So this 1 represents the first toothpick. This 3 represents the number of toothpicks that you add to form a square, right? And this n represents the number of times that you have to add 3 toothpicks to generate n squares. Okay, so the things that I'm saying out loud are the things that I would expect you to be able to describe to me. What are the meanings of each of the terms? What do they represent? Does anybody want to ask me questions about that?
Can you repeat the meaning of n one more time?
In which one? So the meaning of n in all of these is the number of squares Like when I'm thinking about n as the input value, it's the number of squares in the row. Okay. Now, when I'm thinking about the role that it's playing here, though, so like if I'm thinking about the activity that we went through to generate these expressions, technically, this n is really representing in the student's mind the number of toothpicks in the top of the picture, right? And this n minus 1 is representing the number of toothpicks in the middle. And this n is representing the number of toothpicks in the bottom, right? Whereas over here, this n is representing the number of squares for real, right? And the 4 is the number of toothpicks per square. The 4n is the number of toothpicks it takes to make n squares, right? So that's the meaning of this expression. And the meaning of the n minus 1 here is the number of toothpicks that are double counted when you put all of those n squares together. Okay. So each of these rules have sub-expressions, and those sub-expressions have meaning because we have context to this problem. Okay. Don't erase it yet. Okay. I am recording. This will be on YouTube. Okay. I think this is actually the last one. Oh, I was going to bring it back to this, but let's see, do I have time? So this is the conversation that we had at the beginning of class. My question to you now is, how could we use our knowledge of function and function notation to reframe the conversation that we had at the beginning of class? So there's a couple, and there's no right answer here. There's a couple of things that come to my mind, okay? So one thing is that I could, instead of saying what is the sum of, so we came up with a formula here, right? The sum of the first n even integers is n times n plus 1, right? Okay, well, I could replace that sentence with a function. I could say, let f of n equal n times n plus 1 represent the sum of the first n even integers. Okay. And that would allow me to do things like talk about, I don't know, the sum of the first 10 even integers, or the sum of the first 100 even integers, without really having to do a lot, right? Now I could also define a function that would be more interesting. So let me define a new function. Let me define g of n to be n times n plus 1 divided by 2. And this represents the sum of the first n integers. Okay? So when I get down to part C and I'm thinking about this guy, well, the left-hand side of part C is literally 6 times the sum of the first n integers. And I can capture that using function notation, right? 6 times the sum of the first n integers, right? Well, we know the value of that output. And now we're back to what we wanted. Okay. Now if I wanted to ask questions about, you know, I don't know, 7 plus 14 plus 21, right? I have a really easy way of doing that. That's 7 times g of n. right? If I factor out the 7, I'm left with 7 times the sum of the first n integers. Okay? So function notation, again, it just gives us a tool. It gives us a tool to capture a lot of information in a really compact notation. Okay? Okay. So we did a lot today. This was like a crazy big day for us. As always, I'm going to post your homework as soon as I can, but I want you to hand back your tests. And if you turned your homework in, some people didn't. So if you